Lesson 28 is about simulation. So the first simulation that we're going to do in class centers around the exponential distribution and maybe the Poisson process. And so the intent of this video is to sort of get you going and understanding the mathematics behind why we're using the exponential distribution and what the Poisson process actually is, and how we use it in order to do simulations. And so that's the intent of this video. So it's a little more mathy maybe than some of the other ones, but that's okay because in class we'll worry about the programming aspect of it. Okay, so let's start off with what a stochastic process is. So it's a counting process. If this n of t with t greater than 0 represents the total number of events that occur up to time t, or in that window of time t. The most important counting process is known as the Poisson process, and that's sort of why I'm underlining it here, and that's the one that we're talking about today, which is defined as follows. Basically, this n of t greater than 0 has a rate of alpha, and we'll talk about alpha here in a second when we get to an example with alpha greater than 0 if. So it's a Poisson process if these things sort of are true. N of 0 equals 0. So in other words, if there's no time piece to it, then there is no chance. So basically what we're trying to say is there's no chance of getting multiple rivals all at the same time. That's sort of the idea behind there. The next one is that different increments. So if I had different time periods, the number of things that kind of occur inside each one of these things are independent of each other. The next one is that the total number of events in any interval of length t has a Poisson distribution, right? So that's a different distribution, maybe than well, obviously than the exponential distribution. So let's talk about it real quick. And so I'm just going to use sort of the lingo in probability and statistics. So I'm going to define a random variable as the number of events. So the number of events that occur in time t, in some time interval, time t. So because of this property here, the total number of events in any interval of length t has a Poisson distribution. So we're going to say the random variable x is Poisson with alpha t. So that alpha times t is the only parameter that we need. All right, that's the expected value. So mu is equal to alpha times t is the only parameter needed for the Poisson distribution. All right, and then, so what does that look like? So I just want to kind of describe what we're talking about here, maybe on a sort of a temporal piece here. So maybe something's happened up to time s, right? So we don't care what happens up to there, and then maybe this is t plus s, so that this length of time here is t. So if t plus s minus s, obviously that would be length t. So we want to say that the probability that n of s plus t, right, where this is the amount of time minus the number of s is equal to x. So the probability that the number of events, so you can just sort of throw in there. Okay, of course I have 3 in here, little x's, so those represents the time that this occurs, the time that one occurs, and the time that one occurs. Maybe there was only 3 things that happen inside there, but realize that it could be an infinite number of things that could happen inside here, depending on what alpha is and everything else. But obviously the probability of that occurring is very, very, very small. But so we want to be probability. I say that this is the probability that the random variable x is equal to some x, and because of this last piece here, that we know what its actual probability is. It's a Poisson distribution, and what does a Poisson distribution looks like? It's just e to the negative alpha t, what is it? Alpha t to the x, right? So whatever this value is that you're trying to calculate the probability with respect to over x factorial. So that is the probability that we're talking about here. Um, okay, well, let's just go down. Let's visit an example problem. So maybe you guys have seen this before. So say that customers arrive at an ice cream parlor according to a Poisson process at the rate of two. Hopefully this will sort of help you understand what's going on here. So 2 per hour, right? So we talked about it could be 3 per hour, 4 per hour, but in this particular case, we're seeing 2 per hour. And then we want to find some kind of probability of the number of things that occur inside some time window. So in this case, we were saying between 2 and 4 p.m., but it could have been between 3 and 5 p.m. or whatever. But we want to be able to find the probability in those 2 hours, right? So we have to calculate how long that is, and we also want to find the PM, right? So we want to find the probability mass function for this distribution. And so the first thing you do is you calculate what mu is. So think about that for a second. If customers are arriving 2 per hour, and we're talking about 2 hours, obviously we would expect 4 customers. Here, let me use the same color. We would expect customers to arrive. Why? Because we expect them to arrive 2 per hour, and it's 2 hours. Hopefully that may sort of make sense to you of why it's alpha times t gives you the expected value. Now the problem is it's random. It's not going to happen the same way every single 2-hour period. Hopefully that makes a lot of sense to you, because it is a sort of a, like, we know on average how things happen, but that doesn't mean that it's always going to occur on average. For example, rolling 2 die, you're never going to get the average, which is 3.5. But if you kept averaging those, you would. So in other words, if I had a whole bunch of 2-hour periods, I would expect to get 4 customers in an average of all those suckers. Okay. We would expect. Okay, yeah. So I just described what I was talking about here. So then I gave you the random variable. So the random variable x in this case is the number of customers between 2 and 4 p.m. And we know x is a Poisson with a 4 as my mean value. So let's calculate the probability of no shows, right? So what does that mean about a little small x, right? So I'm trying to find the probability that the random variable x for those 2 hours is equal to 0, right? So that's the little small x that we were talking about. So let's just use our, let me see, let's just use our formula here. It's pretty straightforward. So 4 being the alpha t to the 0, e to the negative 4 all over 0 factorial. So that's pretty easy. 0.01. I already did the calculation. I had to get my calculator obviously out for this, and it's 316. So this is about 1.8% of the time for those 2-hour periods you would get 0 customers. Hopefully that makes sense. I mean, because again, we're expecting 4. But the next question is, what is the probability mass function? So how would I get that? Well, what is a probability mass function? Hopefully everyone remembers what these are and how to get them. And so maybe this is x, our little small x, and this is, I'm just going to write PMF up here, probability mass function. And then I want the probability that x, right, the random variable x is equal to whatever our x value is, right? So x can be 0, x can be 1, x can be 2, x can be 3, all the way out to some, basically you could go to infinity, but but obviously as the numbers get smaller, these go to 0. Just by, you can kind of look and see what it looks like there. All right, so so what would be 0? So it'd be 4 to the 0, which we've already calculated, e to the negative 4 over 0 factorial. The 1, let me put a little line here. That would be 4 to the 1, e to the negative 4 over 1 factorial. 2 would be 4 to the 2, e to the negative 4 over 2 factorial. And so on and so forth. 4 to the 3rd, e to the negative 4 over 3 factorial. Okay. And obviously, I don't want to calculate all of this because I'm sort of semi-lazy on that. So I want to obviously let Python do that for us. Let's do that. Let's come up with, here, let me go here to bring us up a new Jupyter notebook. 46 courses, lesson 28, and we'll get a new Python notebook. So obviously we want to import numpy as np. Let's see. And then what do we want to do? I want to write a function that will do exactly this. So we needed to, we're going to call it Poisson. Not, that's not like name is any. And then what do we need? I need the number. So capital N, maybe alpha, maybe time. Let's see, what else do we need to in order to calculate this thing? So alpha, time, N is the number that we're going to do. Maybe that's all we need. So let's just kind of calculate this thing. So my first thing is say mu is equal to alpha times t, and then 4i in range. Oh, I need to find something to calculate. So we're going to call it answer. Answer is equal to np dot zeros, and I'm going to put 2 columns in here. I'm going to say I want it to be n rows by 2 columns, right? Let's do that. And then 4i in range of n. So for each one of these, we want to go through and we want to say answer I is I comma 0. So the one on the left, the column on the left, we want it to be just whatever I is. And then we want answer I comma 1. We want the column to be what? So what did we calculate? Let's just make sure that we get it. So I want mu to the ith power e to the negative mu over I factorial. So, and then we can just calculate all those. So let's go back. So I want it to be mu to the ith power, u to the ith power times mu or exponential. So times np dot exponential times mu, and I think it's negative mu maybe. Yeah, negative mu I think it is. Yep, negative mu. And then all divided by I factorial. Ooh, I need to import math. So from math import factorial. Yeah, that works. And then I need factorial I. That's all we need. Close off all my parentheses. I have to usually look at that. All right. And then print, let's see, we'll just print the answer. And oh, we got to return. So return answer, and then we'll print it. So result equals to Poisson, n of them, alpha, what was alpha 2, and think the time was 2. Let's see what happens here. Okay. So that looks like it's the same number that we had before, and you can see, and so if I did result all the rows in column 1, right, our second column dot sum, let's see what that comes up to, 0.99. So obviously we can do more, right? So I can do more than 10. I can do 20 if we wanted to, shift enter, shift enter. Yeah, you can kind of see that this is getting really, really small. And if we did the sum then, we would get almost all the probability, right? So again, this distribution allows it to go out to infinity, but it has a very, very, obviously, if I'm expecting only 4, you know, the probability of getting 100 should be very, very small. So that's the idea behind that distribution. Okay, well, I think that's all I have for this this class. Hope you guys got something out of it, and we will start up here in the next video.